In our last classes, we dealt with alkaloids and its introduction. We have seen that alkaloids are organic bases which are in most of the cases insoluble in water. They have bitter taste and in most of the cases they are levorotatory, that is specific rotation is negative, and they are containing at least one nitrogen atom in its heterocyclic ring. They have various uses highly because of their physiological activity. They are used in medicinal purpose or for the treatment of various diseases. And we see that how to elucidate the structure, the features of an alkaloid. So first of all, we have to determine the physical, and by various chemical methods we see how to determine the structure. To determine it, we have to first calculate the empirical formula from where we can know how much carbon, nitrogen, oxygen are linked with the ring and how many number of double bonds or triple bonds over there, then which functional groups are present in the alkaloid. Is it phenolic OH, alcoholic OH, ketone, acidoxy, methoxy or whatever. Afterwards, the nature of the nitrogen. Is it primary, tertiary or secondary or amide? Like that. Then some degradation method was followed like MD degradation, Hofmann exhaustive methylation. After it, we can determine the carbon skeleton, the structure of skeleton. Then by following some oxidation reactions or reduction reactions, we can finally determine the structure, and it is confirmed by the synthesis, various synthetic methods. So today we will deal with the nicotine. It is also an alkaloid, and nicotine is the base known and most widely distributed of the tobacco it is actually most widely distributed of the tobacco alkaloids, right? Next is, it is usually occurs in the form of minus. In the minus form, we can see it. It has a specific rotation of minus 169 degree. It is usually occurs in the form of its salts with malic and citric. So in the form of salts of malic and citric acid, it is actually occurring. Regarding isolation, the powdered tobacco leaves are extracted with water and the alkaloids liberated by adding alkali. Then it is steam distilled. The crude nicotine is purified through the fractional crystallization method and of its salts like oxalate. Regarding structural elucidation, first of all we have to determine the molecular formula, which is C10H14N2, and it behaves as a di-tertiary base as it forms two isomeric methyl iodide addition products. So from the form as it is forming the two isomeric methyl iodide addition, so we can say that it behaves as a di-tertiary base. Next is, it is on oxidation with chromic acid or potassium permanganate, it gives a nicotinic acid, which is actually pyridine beta carboxylic acid. So at alpha and beta, this is the beta position, carboxylic acid group is linked over there, so it is beta carboxylic acid, pyridine beta carboxylic acid. Therefore alkaloid contains a pyridine nucleus with a complex side chain at the third position, 1, 2, 3. This is the third position. Next is, when nicotine is heated with concentrated HI at 150 degrees centigrade, methyl iodide is formed. Right? Methyl iodide is formed. Thus the side chain contains N-methyl group. Side chain is containing N-methyl group. And this method is known as Hertzsprung-Meyer method. So by this method we can conclude that the nicotine is containing N-methyl group at its side chain. So after this we can conclude that the nicotine may have these two structures, either this one or this one, where only difference is here extra methyl group is linked. Here the total is C5H10N and here it is C4H7N CH3. So it's the side chain, but this is confirming that it is the basic structure is linked with the pyridine ring. Next is when the nicotine zinc chloride. So this is nicotine C10H14N2 dot zinc chloride. So when nicotine zinc chloride is distilled, the products are pyridine, pyrrole and methylamine. Pyridine, pyrrole, methylamine. This suggests that the side chain is our C5H10N or C4H7NCH3. So the side chain C5H10 is actually a pyrrole derivative. This pyrrole nucleus is probably a part of the side chain attached to the beta or third position of the pyridine ring. So the pyrrole ring is attached to the third position of the pyridine ring. And this pyrrole nucleus is probably a part of the side chain which is attached to the obviously third position of this pyridine ring. So this should be linked with the third position of this ring. So it is clear to all. Our next thing is when nicotine isometh iodide undergoes oxidation with potassium ferricyanide, it forms nicotone, which on oxidation again with CrO3 gives L-hydrogenic acid. So by that reaction we can conclude that 2 or alpha position of N-methylpyrrolidine. So this is N-methylpyrrolidine. So here the 2 or alpha position, 1, 2, that 2 or alpha position of N-methylpyrrolidine is attached to beta or third position, 1, 2, 3, beta or third position of the pyridine nucleus. So here the 2 or alpha position is linked with the third position of the pyridine ring. So by that way you can conclude that if the hydrogenic acid is this one, nicotine should have this structure and the nicotine isometh iodide should contain this type of structure. When nicotine is treated with bromine, C10H14N2 nicotine, bromine treatment in presence of HBr, it forms dibromonicotine, which on heating in presence of barium hydroxide breaks down into nicotinic acid, methylamine and malonic acid, right? So alpha position, again we can conclude that alpha position of the N-methylpyrrolidine unit is linked to beta position or third position of pyridine. So alpha position and beta position of this pyridine. Again this is the conclusion. And last and final confirmation is by synthesis. The following synthesis is due to Path and Brisnader established the structure of nicotine, in which they have taken the succinimide, which on electrolytic reduction yields the 2-pyrrolidone reduction. So this keto group has been out and yielding the 2-pyrrolidone, which again undergoes methylation in presence of dimethyl sulfate. So here one CH3 group is attached with the nitrogen and it is the N-methyl 2-pyrrolidone, right, which on treatment with ethyl nicotinate, they are combining with each other and yielding this type of compound, which on again reaction with HCl in presence of 130 degrees centigrade, this product C, which after decarboxylation the COH has been gone, this product again with treatment with zinc in presence of OH minus, this will yield that double bond O will convert to OH, which on further reaction with HI at 100 degrees centigrade, this type of product where the iodine will be attached in substituted by OH, so OH will be go out and iodine will be linked with this carbon, and finally in presence of base it will cyclize. So after cyclization the plus minus nicotine will be our yield. So this is actually the synthesis. You have to memorize this one. Finally, the path et al. Have resolved the structure by means of tartaric acid, the plus tartaric acid, and the synthetic minus nicotine is identical with the naturally occurring nicotine. But at last the structure also confirmed by NMR and IR spectroscopy. So this is the way we can determine or elucidate the structure of nicotine. So finally, by determining the molecular formula, the nature of nitrogen, then few oxidation process, Herjig-Meyer method, afterwards distillation method, treatment with K3FeCN6, and lastly bromine in presence of HBr. So following this, all that chemical reactions and synthesis by path et al. Confirm the structure of the plus minus nicotine. So this class is finished for today. Thank you.